Our solar system lies in the outer atmosphere of the Sun, the star that powers our Earth's environment. Heliophysics is the study of the Sun and its interactions with Earth and the solar system. The Sun is composed mostly of hydrogen and helium, along with trace amounts of heavier elements. The Sun's corona is so hot that these atoms lose their outer electrons and become electrically charged ions, which, along with the electrons they lost, are expelled from the Sun, creating the solar wind plasma, a flow that streams 1 million tons of matter away from the Sun every second. Scientists have only recently been able to observe high-latitude solar wind. During the solar minimum in 1994, the Ulysses spacecraft encountered near-uniform fast solar wind over the magnetic poles, where the solar wind flows out unimpeded since the magnetic field lines are open to the heliosphere. When the Sun's activity increases towards the solar maximum, this fast polar wind disappears and the magnetic field structure becomes more chaotic as the Sun's magnetic poles reverse polarity. As the solar cycle returns to the minimum, the magnetic poles reposition over the Sun's rotational poles and the fast polar solar wind reappears, but with the opposite magnetic polarity. As this solar wind streams out in all directions from the rotating Sun, like a spiral of droplets from a lawn sprinkler, the charged ions in the solar wind are bound to magnetic forces, thus carrying the Sun's magnetic field in spiral shapes outward through the solar system. This outward flow of solar wind largely fills the vast space between the planets in our solar system. Magnetic plasmas don't mix, so the solar wind plasma pushes against the interstellar medium, which is the plasma between the stars in our galaxy, and carves out a bubble-like atmosphere shielding our solar system from the majority of galactic cosmic rays. The point where the solar wind begins to interact with the interstellar medium and slows down is called the termination shock. NASA's Voyagers 1 and 2 spacecraft have reached this innermost boundary of the heliosheath, which is twice as far from the Sun as Pluto's orbit, and are expected to reach the outermost boundary of the heliosheath, the heliopause, in the coming years. This bubble, or heliosphere, travels through the interstellar medium, creating a bow wave or shock, and leaves behind a long heliotail in its wake, much like a boat traveling through the water. While the boundary prevents any interstellar plasma from entering the heliosphere, some cosmic rays can get through. The amount of these cosmic rays that enters our heliosphere varies during the solar cycle. During the prolonged solar minimum in 2009, the highest level of cosmic rays in the space age was recorded. In addition to cosmic rays, neutral atoms from the interstellar medium also get through the heliosphere and mix with the charged particles of the solar wind at the heliospheric boundaries. As a charged ion interacts with a neutral atom, it can capture an electron and become neutral itself. This exchange does not impact its direction or speed, but it is no longer bound to magnetic forces and travels in a straight line. Atoms of hydrogen can reach as far into the solar system as the Earth, where NASA's Interstellar Boundary Explorer, IBEX spacecraft, can detect and chart the origins of these energetic neutral atoms, ENAs, creating an all-sky map of the boundary. These spectacular maps from IBEX found that most ENAs originate in a band or ribbon that spans the entire sky. This ribbon is linked to the magnetic field that exists outside the heliosphere in the interstellar medium. NASA's heliophysics missions are continuing to collect data about the solar wind, its particles and magnetic fields, and the boundary of the Sun's influence in space.